Hello, linear algebra students. Okay, so we're going to look at section 1.2, row reduction and echelon forms. Okay, so first, a definition I actually gave you in the last video, but I need to reinforce it here. A leading entry in a matrix, okay, is the leftmost. I'm going to write it a little differently than I wrote it the first time, give you two ways to think about it. The leftmost non-zero entry in a row. Okay, so it's the first non-zero entry. I said the first last time, wrote leftmost this time. So the leading entry in a matrix is the leftmost entry. Okay, and again, we're looking at creating triangular matrices so we can determine the solution to a set of linear equations or a system of linear equations. Okay, so we're going to have two terms here. First is going to be a row echelon form. A row echelon form. Sometimes you will see that just called echelon form, leaving off the row part of it. But row echelon form is how I'll refer to it, and that is REF is our abbreviation for it. Okay, and so three characteristics of a matrix in row echelon form. Okay, so the first characteristic: all non-zero rows are above any zero rows. So a zero row is a row that contains only zeros. So all non-zero rows are above any zero rows. Okay? So any rows that are just zeros all the way across are at the bottom of the matrix. Okay. Second, each leading entry is in a column. So remember, columns are the vertical pieces. It's in a column to the right of the leading entries in the rows above it. Okay, so each leading entry is in a column to the right of the leading entries in the rows above it. Okay, so when you're looking at those leading entries, they move to the right. That same triangular pattern we talked about with triangular matrices in section 1. Okay, and then our third characteristic is all entries below a leading entry are zeros. Okay, all entries below a leading entry are zero. Okay, so let's look at a couple of matrices here. 1, 2, 3, 4. 0, 1, 2, 1. And then zeros across a bottom row here. So as I look at this matrix, right, the only row of all zeros is at the bottom. Okay, so that satisfies condition 1. Okay, my two leading entries here, this second one is to the right of the first one. Okay, and then if I look at my two leading entries and I go below them, I get 2 zeros below that first one, and below this second one I have 1 0. Okay, so these are fine because they're not leading entries, right? This 3 has a 2 below it, but it's not a leading entry, so that's not an issue. Okay, another example. Okay, so in this one, this is not in row echelon form, okay, because I have a leading entry here. Okay, that's fine. This is a leading entry, which is okay, so I'm looking fine now, but this third leading entry moves back to the left, okay? But as I look at this matrix here, what I could do is do a row operation, right, where I interchange rows 2 and row 3. And when I do that, get that written down there. So once I do that interchange operation, now I have a matrix that's in echelon form because I have this triangular pattern again. Okay, I have 3 leading entries. They line up to the right. I don't have any rows that are all zeros, so I don't have that to worry about for condition 1. And each of these leading entries has zeros below it. This 2 has 2 zeros below it. This 1 has a 0 below it. And this one has no numbers below it, so that's fine as well. Okay. All right, so that's row echelon form. Now, I said there were two forms we were going to look at, and this second form is called reduced row echelon form. Okay, abbreviated RREF. A reduced row echelon form. Now, you'll also see it just as written as reduced echelon form. I don't like that because it gets confusing with having two things that are perhaps just REF, row echelon form, or reduced echelon form. So I try to use reduced row, so it's 2 R's is the reduced form. Okay? And so so a reduced row echelon form is still in row echelon form. You see those same words there. So I'm actually going to start with 4 here when I write down the characteristics, because 1, 2, and 3 still apply to this matrix. Okay, so 4 then is going to be that the leading entry in each non-zero row is 1. The leading entry in each non-zero row is 1. Okay. And then fifth, so the condition 5 then, each leading 1. Okay, so notice in condition 4 we said the leading entries have to be 1. So now for condition 5, I just say each leading 1 is the only non-zero entry in its column. Okay, each leading 1 is the only non-zero entry in its column. That is condition 5. Okay, so if I look back at my examples for row echelon form, okay, I have the first 3 conditions just like we talked about, but now, and I have 1s here, so condition 4 is met for this first example. But condition 5, if I look at this 1 and go up, I don't have a 0 there, okay? So you have to also go up from your leading entries in reduced row echelon form, okay? Same type of thing here in the second example. Once I've done the interchange, if I look up from that leading entry, I need to get zeros above those leading entries, okay? So something in reduced row echelon form, maybe we have something simple. This would be a really easy system to solve because it's basically already solved for you, right? We would have this x1 equals 3, x2 equals 2, and x3 equals -1. And so as I look here, I have the leading entries are all 1s, just like I need. They move to the right, so I need to be in row echelon form. And if I look above or below each one, so that 1 has only zeros with it, that 1 has only zeros with it, and then the third one has only zeros above it. Okay, I don't have a leading entry in this column, so I don't have to worry about the fact that I don't have a 1 or things there. Okay. Now we can also have some slightly more tricked up RREF matrices. Okay, so again, my only leading entries here are 1. They're those 2. I have a row of all zeros in the bottom row, so that's fine. Remember, they're at the bottom. As long as they're at the bottom, it's good. Okay, and I look below this 1, I have all zeros. I look above and below this second leading entry, and I have all zeros. There's no leading entries in these columns, so I don't have anything to worry about there. Okay. Okay, so make sure you meet all 5 criteria. Let me write out another one here. Okay, so as I look at this one right now, I have not met all the criteria because I have 3 leading entries. That's fine. Okay, so I'm in row echelon form. My 3 leading entries move to the right. I don't have any rows of non-zeros. So REF I have covered, but our REF I have not yet met. Okay, because This leading entry here, the second one, is not a 1, it's a 2, so that's a problem. And this bottom one is a 1, which is fine, but above it, I don't have zeros, okay? Okay, so we're going to look at this matrix just a little bit more here on the next page. But first, give you an important theorem here that we want to mention. So this is theorem 1 from this section. Okay, and theorem 1 says each matrix is equivalent to 1 and only 1 reduced row echelon form. And I'll write RREF in parentheses there to remind you that's what reduced row echelon form is. The one and only one reduced row echelon form matrix. Okay, so there's only one matrix that we can reduce. You know, there's lots of row operations, lots of different types of row operations we can do, but if we get it to reduced row echelon form, it's going to be a particular matrix. Okay, and that's important because that means that our systems that we do have one solution, right? When I get that to reduced row echelon form, I'll have a unique single, I shouldn't say unique, I will have a single expression for the solution, okay? It may correspond to multiple solutions, but it will be a set of solutions that is distinct to that matrix, to that system, okay? All right, so let me write down that matrix again that we had. 1, 0, 3, minus 1, 2. The third one we finished on the last page that we said was not in reduced row echelon form. It is in row echelon form, but not reduced row echelon form. Okay. So we want to do row operations on this matrix, okay, because I want to get this to reduced row echelon form. Okay, so as I look here, my second row, these are all even numbers. So I can quickly get this leading entry to be a 1 merely by dividing everything by 2. So I'm going to take row 2 and divide it by 2, and I'm going to replace row 2. I'm going to use the tilde there to represent an equivalent matrix. So my equivalent matrix has the same row 1. Row 2 then is divided by 2. And row 3 then is the same as before, okay? Now, so my first column, I have my leading entry 1, that's good, zeros below it, good to go. Second column, I have my leading entry 1, zeros above and below, so we're good there. Now my third column, I have the leading entry 1 like I want, but I need zeros above that column, above that entry, okay? So I have my 1, I'm going to get a 0 right above it in place of that 2. So I need to take negative 2 copies of row 3, add them to row 2, and replace row 2. Okay, because that will get me a 0 for that entry that is immediately above the 1. Okay, so equivalence again. Row 1 is unchanged. Row 2 now, this is 0 plus 0 is 0. 0 plus 1 is 1. Negative 2 plus positive 2 is 0. This is going to be a negative 2 times a negative 1 is a positive 2. 2 plus 3 is going to be 5. Negative 2 times a negative 2, that's a positive 4, and 4 plus 4 is going to be 8. Row 3 then doesn't change. Okay, now I need to do the same thing for the 3 that's above my leading entry of 1. So I'm going to do negative 3 times row 3 plus row 1, and I'm going to replace row 1. Okay, so I'm working my way up here. I've got 0 plus 1 is still going to be 1. 0 plus 0 is still going to be 0. I've got negative 3 plus 3 is going to be 0. Negative 3 times a negative 1 is a positive 3. Minus 1 is going to be a positive 2. Negative 3 times a negative 2 is going to be a positive 6. Plus 2, that's going to be 8. Okay, row 2 then is unchanged. Row 3 then is unchanged. Okay, so I have my matrix now. Now I'm in reduced row echelon form. Okay, I have leading entries that are all 1. They move to the right. I have as many as I can possibly have. I don't have my 0 rows are at the bottom. I don't have any, so they're at the bottom proverbially. Okay? These columns don't have a leading entry, so it doesn't matter that they're not all zeros and ones. Okay, so that is reduced row echelon form. Okay, again, look through your book for some other examples. Right, when you look at the homework problem, you'll get some other ideas as well. Remember to complete those homework assignments in my math lab. Okay, that can add up to a lot of points for you in the class. Okay. All right, so these important spots here, these leading entries, we're going to give a name to. Okay. So a pivot position is a location in a matrix corresponding to the leading ones in the reduced row echelon form, the RREF of the matrix. Okay? Now, you use the reduced row echelon form to identify where those pivot positions are, but those pivot positions are the pivot positions for any matrix that has that form. So we go back to the one we reduced here with these ones that I circled as the pivot positions. Okay, those are the leading ones in the RREF. Well, that means back in my original matrix, my pivot positions were in the same locations. Okay, so that 1, 2, and 1 then are the pivot positions. Okay, so you can swap out a lot of language about leading entries for pivot positions. Okay. Then we'll also say a pivot column is a column that contains a pivot position. Okay. So if we think about the really relatively simple matrix that I started with and some of the systems that we solved in the previous section, and if we think about something like that simple matrix that I had on the last page, my pivot positions are already very easy to identify. It's where those leading ones are. And we also used that to identify the solution, right, when we did that in the previous section. So x1 was 3, x2 then was 2, and x3 equaled -1, right, if we think of this as an augmented matrix. Okay, so we're going to use that language to help us figure out, again, the existence and uniqueness of a solution. So remember our two main questions, right? Our two main questions. One is, does a solution exist? Existence. And two, is that solution unique? Okay. So when we have a system or when we have a matrix, many times we want to write down a general solution for that matrix or for that system. Okay, that's frequently what we're looking for. That's really the genesis of almost all of linear algebra classes, solving these systems and writing down the solutions for these systems. Okay. So if I take a look at the matrix we just solved, right? Okay, I have this matrix I just solved. Remember my variables? If I want to think of this as an augmented matrix, I know we haven't to this point, but we can. You know, I have my variables. They go left to right, x1, x2, x3, x4. Okay, so I can write down what the solution is here to this system, even though I don't have it cleanly, right? I have x1 plus 2 copies of x4 is equal to 8. I have that x2 plus 5 copies of x4 is equal to 8. And I have that x3 minus 1 copy of x4 is equal to 2. Okay? So as I look here, my x4 is not determined, right? It could be largely anything. So we will usually write down something like x4 is equal to x4. Okay? What that means is x4 is what we call a free variable. Okay, it is not determined. It could be anything. Okay, so as I look at this matrix has a solution. It has a great many of them actually, But that solution is not unique because I can pick any value for x4. Say I pick 0, that's a solution. If I pick x4 is equal to 1, well then I could plug in the 1 here for each of these x4s, and that gets me a different solution. Okay, so the solution clearly exists, but it's not unique. Okay, and so we call this type of thing a general solution. Okay, now to write a general solution, you want to have an expression equal to each basic variable. And when I say basic variable, I'm just saying what your variables are. So in this matrix, I have 4 variables, so I should have 4 equations. I should have x1 equals something, x2 equals something, x3 equals something, and x4 equals something. Okay, so x1 then, if I look at my equation here, I can take the 2x4 to the other side, so I get negative 2x4 plus 8. I can take the 5 to the other side, so I get negative 5x4 plus 8. Okay, I can take the negative 1x4 to the other side, so I get x4 plus 2 in that case, and then x4 is just equal to x4. Okay, now you will also see this written just as x4 is free. Okay, those are both acceptable ways to write it. You have to pay attention to the way the homework asks you for it when you're filling in some general solutions, but x4 equals x4 and x4 is free. Those are interchangeable notations. Okay, so this would be our general solution to that system. Okay, if we look back at a previous one right ahead here, this actually was already a general solution. I didn't have any free variables. Okay, so I already had that written there. Okay, so we have 2 kinds of variables: basic variables and free variables. Basic variables and free variables. Okay, a free variable is one that is not determined. It can be anything. A basic variable is one that depends on the free variables if there are any, or if there's not any free variables, then we say that that solution is unique. Okay, such as that system up there, right? That solution was unique. It had no free variables. Okay, so ultimately the unique question comes down to, are there any free variables? Okay, the existence question depends on where your pivots are. Okay, so if I have another matrix here, it's going to be a relatively simple matrix. Okay, think of this as an augmented matrix again. Okay, well, my pivots are in those 2 positions. Now, this is not in RREF form because I don't have zeros above that pivot. But the thing to notice here is that that pivot is in the far right column. Okay, and if your pivot is in the far right column, then you have no solutions. Okay, so that is theorem 2. Okay, that is theorem 2. Let's get that written down here. A system is inconsistent has no solution if the far right column or rightmost column is a pivot column. Okay, system is inconsistent or has no solution if the far right column is a pivot column. Okay, or there's a pivot position in the far right column. Those mean the same thing. Okay, because if you think about what that augmented matrix form looks like, right, with the equal sign, we're saying 0 equals 1 here, which is obviously a problem. Okay, all right. So what I want to look at now is an algorithm for determining solutions. Okay, and to keep me from going too fast, I usually try to write out these as I talk. So that lets me not go too fast. But I'm just going to put this up here and talk through it, and then we'll talk through a couple of examples using this algorithm. Okay, there's a lot of words, so I didn't really want to rewrite them again. Okay, so our row reduction algorithm. So first step is you always make the leftmost column a pivot with the pivot position at the top. Okay, so you just say we're going to take the top left and make it a pivot. Just gives us a starting place, okay? So you switch your desired pivot to the pivot position. So you look in the leftmost column and you think, okay, what's the best way I can get a 1 up to that top left spot? Okay, then you use row operations to make zeros below it. Okay, and once you have all zeros below, okay, so think about it in terms of the matrices we looked at, right? I've got a pivot here in the upper left. I get zeros below, okay? Then I'm going to go make another pivot, and I get zeros below that. And then I'll make another pivot. Okay, I ran out of them. Okay? And then step 4, cover the row with the pivots and repeat 1 through 3 for the rest of them, right? So you make your pivots across. Then you start at the right-hand side and work your way up. Okay, so you go left and down, work your way all the way across. Then you start from the right and you work your way up. Okay? Now that algorithm is spelled out for you. Let me make sure I tell you the right page number. If you want to write it down from the book, I thought I had it printed. That algorithm starts on page 16. So if you're looking in the textbook, you start on page 16 if you want to write down that algorithm. You can also, of course, pause the video here and get that algorithm written down. I'm trying to get it all in the picture here on my document camera. Sorry about that. So the leftmost column is a pivot. Switch your desired pivot to the pivot position. Use row operations to create zeros below the pivot. Cover the row with the pivot and repeat 1 through 3 for the other rows. Repeat with all the rows. And then starting with the rightmost pivot and working up and left, create zeros above each pivot. And then you also need to make sure you scale the pivots to 1 because that's a condition to be in row echelon form. Okay. All right, like I said, I'm trying to pause here. Pause the video if you need to. Look at the textbook if you want to write down the steps in that algorithm. Okay, we're going to do some examples with that algorithm, of course. Okay, so as we look at this matrix here, 1, 0, -3, 1, 0, 1, 2, 4, all zeros along the bottom row, is already in reduced row echelon form. Okay, remember we can think of this as augmented. Okay, so I would have x1, x2, x3. So there's 3 equations, right? 3 rows, 3 variables because I have 3, and then I have the augmented row, augmented column, I should say. So 3 variables. As I look here, the pivots are in the x1 and x2 columns. That means that x1 and x2 are your basic variables. Since the x3 column does not have a pivot, x3 is a free variable. Okay, so I can write down the corresponding equations for those. Okay, so my solution set here, right? x1 is equal to 1 plus 3x3. Again, I took that -3 and moved it over to the other side. x2, 4 minus 2x3, and then x3 is free. Or we could have written x3 is equal to x3, right? Those are the same notation, same meaning, okay? So that gives us a solution set. That's an explanation of that solution set. Now that solution set is not unique, right? It's not a unique solution because x3 is free, okay? All right. Okay. Now let's look at another matrix here and let's work through this row reduction algorithm. Put this in the right spot here. So 1, -7, 0, 6, 5 going across there, 0, 0, 1, -2, -3. Okay, so as I look here, upper left is going to be a pivot. Perfect. Good to go. I'm going to go ahead and circle it, just to emphasize that's our pivot. So we got that kind of first step taken care of. It's already 1, so not an issue there. So I want to get zeros below it. Okay, so I've already got 1 0 below it, so I need another 0 down here below. So I'm going to take row 1. I'm going to add it to row 3, and I'm going to replace row 3 because 1 and -1 added together will get us 0. Okay, so I've got 1, -7, 0, 6, 5. Right, row 1 doesn't change, row 2 doesn't change, 0, 0, 1, -2, -3. Row 3 now is going to be 0. -7 and 7 makes 0. 0 and -4 makes a -4. 6 and 2 is going to be 8. And then 5 and 7 is going to be 12. Okay, and that's an equivalent matrix to the matrix that I started with. Okay. Now, as I look here, I've got zeros below. Now, my next pivot actually turns out to be here in the third column. Okay, so I don't have a pivot in the second column. Okay, so that's an important reason why we didn't want to switch these rows around early. Okay, there wasn't a need to, okay, because you might think, well, I'm going to need to switch these rows to get a pivot up to this spot. It turned out after I did that operation, there simply isn't a pivot in that second column. So that second column is going to correspond to a free variable. Okay, so again, always work your way down and to the right, down and to the right. And then we will go up and to the left once we've gone down and to the right. So don't worry about going up from this one. You want to go down from this one. So I got to get a 0 here below this next pivot. So I need 4 copies of row 2. Add that to row 3 because 4 and -4 will make 0. And we're going to replace row 3. Okay, so I've got 1, -7, 0, 6, 5. 0, 0, 1, -2, -3. Okay, and then below that, I've got 0, 0. Okay, because 0 plus 0 was 0, and 0 plus 0 was 0. 4 minus 4 is also 0. -8, right? 4 times a -2, and 8 is also 0. Okay, and 4 times -3 is 12. Plus 12 is also 0. So I get all zeros on that bottom row. Okay, so I'm actually out of pivots. Those are my only 2 pivots. Okay, so as I look above these pivots, I've got zeros above it, right? This pivot has nothing above it, so it's fine. This pivot then has a 0 above it, so we're done there. Okay, those are my only columns with pivots. Okay, so the fact that the other columns are not zeros or ones is not an issue. Okay, and so what this means is my system here, I have x1 is equal to 7x2. Remember, I'm using this as an augmented matrix, and I'm bringing that over to the other side of the equal sign. So instead of x1 minus 7x2, I'm just taking it to the other side of the equal sign. So I have a positive 7x2. I have negative 6x4. Again, I'm taking it to the other side of the equal sign, so it's negative. And then plus 5. The 5 was already on that side. 5 was already on that side, so we keep that there. Now, x2, no pivot in that column, so x2 is free. x3 then, okay, that is going to move that -2 over, so I'm going to have 2 copies of x4 minus 3. Again, the -3 is already on the right-hand side, and then x4 has no pivot in its column, so x4 is free. So we'll say x4 is equal to x4. Okay. Now, as I look at this solution, we're going to come up with some ways to write these solutions to maybe look a little nicer. Okay, so as I look here, I have 2 free variables. Okay, so this is a solution set. Perfectly good way to write a solution set. We just want to use all our tools at our exposure. And we're going to start talking about vectors in section 3. We're going to kind of introduce that idea here. So I have a free variable x2. Okay. Well, as I look at these equations, I have various copies of x2. I have 7 in the first equation. I have 1 copy for the free variable in the second equation. That's why I write x2 equals x2. x3 doesn't have any copies of x2, and x4 doesn't have any copies of x2. All right, that fourth equation. Okay. Now I also have an x4. Okay, in x4 I have -6 copies in the first equation, no copies in the second equation, 2 copies in the third equation, and 1 copy in the fourth equation. Then I also have some other numbers sticking out here at the end. I have 5, nothing in the second equation, -3, and nothing in the fourth equation. Okay? So my solutions then are actually the sum of these 3 things, right? So I'm adding these pieces. You say, well, I was subtracting in here, right? So we brought the negative inside of my column matrix there, okay? These are little small matrices called a column matrix, which we're actually going to call a column vector in section 3. So that gives us another way of writing the solution. This also gives us a way to write a parametric solution. So you should have heard about parametric equations somewhere along the way in calculus. I said parametric equation, so I wrote it, but I mean parametric solution. And we can write this as a parametric solution. And what a parametric solution means is we're just going to use a parameter, okay, which usually our parameter we represent with time, t. And a lot of times then a second parameter would be used with s, simply because it's a letter near t, or r because it's a letter near t. Okay, t for time usually as it pertains to parameters. So we might write this solution with t times my first vector, s times my second vector, and then this constant on the end here is simply constant. So it doesn't have a parameter because it is a constant. So I have two parameters there, s and t, and they're good to go. Okay. Let's look at one more of this type. A little more ornate. Okay, so I have this matrix here. Okay, I want to do some row operations. I want to get it to where I can write the solution set. Okay, so I'm going to use my row reduction algorithm. So I make the top left a pivot. Okay, now you can go ahead and scale it, but as I look through here, if I divide that by 3, I'm going to make a bunch of fractions. So I want to put that off kind of as long as I can before I start making those fractions. Okay, so I want to get zeros below it. Okay, so I've got -9 here. So I'm going to do 3 copies of row 1, add that to row 2, and replace row 2 because 3 times 3 will be 9, and 9 minus 9 will be 0. So my first row is unchanged, 3, -4, 2, and 0. Below that then I've got 0, because 3 times 3 is 9, 9 minus 9 is 0. 3 times 3 is a -12, and minus 12 plus 12 is 0. And then the same thing here, 3 times 3 is 6, minus 6, that's also 0. Okay, and then my third row is unchanged. Again, we use that tilde to indicate an equivalent matrix because we did a row operation. Okay, now I've got a row of all zeros, so I want to take that row of all zeros and get it to the bottom. So I'm going to interchange row 2 and row 3 because I know I need that all zero row at the bottom of my matrix. I take row 2 down to row 3. And then there is my row 3 up to my row 2 now. Okay, now I still need to get zeros below my pivot. Remember, 3 is my pivot right now. So I'm going to do 2 copies of row 1 and add that to row 2, because again, that will get me 6 minus 6. And we're going to replace row 2. Okay, so 2 times 3, that's going to be 6. So my first row is unchanged. Below that then, I'm going to get 0. 2 times 3 is 6. 6 minus 6 is 0. Times 2 here, I'm going to get -8 plus 8. That's also 0. Times 2 here, I'm going to get 4 minus 4. That's also 0. So I got all zeros on that row and all zeros on the row below it. Okay, so I actually have 2 free variables for this system, right? Now I need to go ahead and divide by 3 because I need to get that to be in reduced row echelon form. So I got to have that leading 1. But if I had done that earlier, then I would have had to deal with those fractions as I was doing those replacement operations. So it's much easier to wait on that if we can help it. And I didn't write down what we did there. We did row 1 and divided it by 3 and replaced row 1. So we did a scaling operation. So as I look here, I have x1 is equal to 4/3 x2 plus, minus, I should say, because we're moving it over to the other side of the equal sign, 2/3 x3. Remember, this is augmented, so it's got to go to the other side of the equal sign. And then it'd be plus 0. We won't write the plus 0 down because that would be silly. x2 then is free, and x3 then is free. Okay? So then I can write this as a vector solution, right? I've got x2. I have 4/3, 1, and 0. I got x3. Has -2/3, doesn't have any in the second spot, and then 1 there in the third equation. And then I actually don't need a plus a constant here because I don't have any constants stuck on the end of this equation. Okay, and then we might also write a parametric solution, right, using, say, t in place of that and s in place of x3. Okay, Now, a couple of homework questions just to be aware of. One of them talks about an interpolating polynomial. It has kind of a bunch of words setting it up. When you are looking at that interpolating polynomial, and then I had it here to share with you. I was just going to show you that question. But what I want you to do when you're looking at those word problems is to make sure that you just read through the question. There's going to be something embedded in the question about what we're dealing with, okay? Sorry, I thought I had it open here. Okay, so I'm going to switch over here. This interpolating polynomial question here. So if you look at this, there's actually a system embedded here, okay? So it's giving you some data, okay? So you have x coordinates, right? So you see that's 1, 2, and 3 there, 1, 2, and 3 for your x coordinates. Then you see these y coordinates are over here on the other side of the equal sign. So this actually corresponds to a system, right? A0 is, say, your x1, a sub 1 is like your x2, a sub 2 is like your x3. Okay, so you can actually set up a matrix system here to work with, okay? So x1, x2, x3, and then on the other side for your augmented matrix, right? So here, this first row, right, we would have 1, A0, 1, A1, and 1, A2, and then 12. So that first row, right, would be 1, 1, 1, 12. Your second row then would have 1, A0, 2 A1s, 4 A2s, so it would be 1, 2, 4, and 15. And then your third row, right, would be 1, 3, 9 for 3 squared, and 16. Okay, and then you're just solving that matrix. Okay. Now, honestly, there are many ways to solve matrices. Okay, and we will absolutely be looking at some of the calculator methods as we go. And so, ultimately, in the online homework, you don't inherently have to do every step. That's just the nature of online homework. So feel free to use that to your advantage if you need to. Now, as you look at quiz questions, and even some of the homework questions ask you about what the next row operation is supposed to be and things like that. So you do need to have those row operations in your toolkit. But ultimately, if you're just solving the system, you can use some technology at your disposal. And we will be looking at some of those technological tools as we go to future sections. Okay, so that's going to finish our 1.2 video for the day. Remember, look at your homework assignments. Please let me know if there's anything I can do to help in furthering along our online course. Have a good day.